The Earth's geological time scale, 4.6 billion years of history. Every millimeter on this scale is 1 million years. So 4.6 billion years is 4.6 meters. The first life on Earth, the first evidence we have of life on Earth is 3.5 billion years old. That's here. Cyanobacteria. From this time up until you could see life without a microscope in the Ediacara, all of life on Earth was cyanobacteria or other single-celled algae. First in the Ediacara, you could see life without a microscope. And that's where we expand these last 635 million years. We've expanded 100 times, so we get this big scale with a lot more detail on it. So here in the Ediacara, there's only soft-bodied animals, no hard shells. But first, and then in what we call the Cambrian, we get hard shells evolved, and then we get a lot of fossils preserved. On our scale here, we see the average sea level on the entire Earth, and we see the paleogeography that we can deduce from mapping of sedimentary rocks and others. And on the bottom here, we see the magnetic polarity. The Earth is like a large magnet, and it's shifting its north and south poles irregularly. And sometimes it's black, like it is today. This is a regular polarity, and then it will reverse and become reverse polarity. And this is useful commercially for mapping sediments, correlating sediments. We notice here on the paleogeography, Balticum, Norway, Sweden and Finland was very far south. In the Ediacara, we were almost at the South Pole. We've been moving north ever since, about 2 to 4 centimeters a year. And in the Ordovicium, where we have a lot of marine sediments preserved in Norway, we're still quite far south of the equator. We're moving northwards all the time and passing through different climate belts. And climate produces different sediments. So, for example, when we're here in the Devonian, we're south of the equator in the subtropics. And at the same time, there's an enormous mountain chain just to the west that was caused by the collision of Europe, the European plate with the North American plate. It pressed up the largest mountain chain on land in Earth's history. And the erosion of this provided the first sediments on the Norwegian shelf. So here in the Devonian, this is also where we have the oldest, geologically oldest petroleum reservoir producing in Norway. When we pass into the Carboniferous, this mountain chain is more or less eroded, almost flat. And we have very low-lying lands. We have coal deposits, for example, in many parts of northwest Europe. And ice age in the southern hemisphere with a large ice cap. Then we go into the Permian, where all the continental plates have coalesced into one supercontinent. And more or less, continental drift locks up, so we have very low sea level. There's no sea force spreading to speak of. So the ocean basins expand or sink, and so we have extremely low sea level. We have an enormous extinction of life. At this boundary between the Permian and the Triassic, about 95% of the number of species disappear. So here is a dead zone in the Triassic, and it's filled up quite quickly with animals that did survive that mass extinction. And for concerning Norway, we have a very arid climate, and we have a lot of river deposits on the Norwegian shelf, and also commercial reservoirs in those river deposits. We come into the Jurassic, we're still moving north. We're north of the equator now, about the same latitude here in the Middle Jurassic as northern Italy is today. Very nice climate. We have enormous delta deposits between present-day Norway and Scotland, and about 65% of Norway's petroleum reserves are found in these delta deposits of the Middle Jurassic, about 175 million years ago. Then these are covered by sea, and in the late Jurassic, we have our source rock, black clays, organic-rich, microplankton-rich black clays. And I have, as a matter of fact, photographs. This is microplankton deposited here from the late Jurassic on the Norwegian shelf, and this is what gives us our petroleum, plankton like this. And we have also bacteria that's degrading that plankton into a jelly. And when this jelly is warmed up to 100 and 130 degrees, it becomes liquid, hydrocarbon liquid. So this is actually the raw material that's extracted from black clays right about here, and where the Norwegian shelf was located in the late Jurassic. So then we go into the Cretaceous. This black clay deposit stops, and we get regular marine deposits the rest of the time, and the sea level is constantly rising. South America and North America are spreading. Africa is breaking off North America, so we get the beginning of the Atlantic Ocean that's getting bigger and bigger. And seafloor spreading is intense, and we get extremely high sea levels because of this intense spreading of the continental plates. And the 65% of life on Earth again dies out here. The dinosaurs, among others, disappear, and we have the age of mammals, which get big very fast. And on the Norwegian shelf, we have even here some commercial deposits and sandstones. And moving on to the Neogene, late in the Neogene, climate becomes cold again, the Pliocene, and we get what we call today the ice ages in the last, say, 3 million years, where we have ice caps on both the North and the South Pole at the same time. That's actually quite rare. To the end of our scale, we have the present day. All of human history, written human history from the first civilization in the Tigris, Euphrates Valley, the first written languages, first agriculture, would comprise the last 0.6 millimeter on this time scale. And that's what we call history.